Hi, today I'm going to be giving a tutorial on how to use machine learning to make digital copies of real-world amplifiers and guitar pedals. I'm going to run through the steps without really explaining why we're doing what we're doing. This is just a step-by-step guide that anybody, even without programming experience, can follow and hopefully do this on their own computer. We'll be using Windows 10 to do this. So first, I'm going to direct you to the code repository that we're mainly going to be using for the model training. I'm going to include all of these links in the notes in the YouTube video, so don't worry if you don't catch the address of these pages. So what we're going to do is download this code by clicking the green code button and clicking download zip. If you have Git and want to get the repository in that method, you can use that too. But I'm trying to make this tutorial for anybody that doesn't necessarily have programming experience. So we're going to go with the download zip option. And there it goes. It may take a few minutes. There are some audio files in this repository that make it a little bit larger, about 30 megabytes. So we're going to take this zip file, and I'm just going to put it right on the desktop. You can put it wherever you'd like. Extract here, there it goes, and open up that newly created file. This is the PedalNetRT repository. RT stands for real time. It's based on another repository that's just called PedalNet that does the model training as well, but this adds a conversion script that gives it real-time capability in a guitar plugin. So within this repository, I included some documents which we're going to be following. So go ahead and let's open those up. The first one we're going to be using is this setup for model training. This will get all of the dependencies that we need to be able to do machine learning using PyTorch. So I'm just going to go step by step through this document. I'd recommend that you open it up and follow step by step if you can't catch everything in the video. So the first thing we're going to do is check the GPU on your computer for cuda capability. Cuda is specific for machine learning, and it's also specific to NVIDIA. So unfortunately, if you don't have an NVIDIA graphics card on your computer, you won't be able to do this. You can still do PyTorch machine learning on your CPU, but it will be very slow. I think this particular model training could take a day or more just on your CPU, whereas using a GPU, even a low-end GPU, will reduce that to 8 hours or less. Still a long time, but there's a lot of calculations going on in this machine learning algorithm. So the first thing that we want to do is check our NVIDIA control panel to make sure that it is compatible with cuda, C-U-D-A. So right-click on your desktop and go to the NVIDIA control panel. Select Help from the toolbar, and then click on System Information and go to the Components tab. So underneath Components, you'll see under 3D Settings, you'll see this line nvcuda.dll, and underneath the product name, you'll see the version, which the numbers we care about is 10.2. So remember the version that's listed there, and that matters with which version of PyTorch we download. So I'm scrolling down in the setup document. So the next step after we have checked the CUDA version on the NVIDIA control panel is to install some dependencies. Now, the way I'm going to do it here is by going through a Python package called Anaconda, which includes PyTorch and a bunch of other dependencies needed for this machine learning. So I'm not going to show that part. It's pretty straightforward. Click on the link under installing Anaconda, go there, download and install the appropriate downloader. For me, it's Windows 64 and Python 3.7. After you've done that, we're going to install PyTorch and PyTorch Lightning, which is it makes PyTorch code much easier to write and to use, and it's much more understandable when you look at the code. And this is what PedalNetRT is using. So we're going to go to this site, the PyTorch Get Started Locally. And we're going to choose the appropriate version. I'm going to be using Windows Conda because we're using that Anaconda environment. Language Python, and the CUDA version, which we noted earlier, for me is 10.2. If it's different, if it's 9.2, 10.1, and we're going to open up an Anaconda prompt by, this is how I do it, by starting to type in Anaconda in the search bar, and you'll get this Anaconda prompt come up. Click that, and it's just a command line within the Anaconda environment. So we are going to copy this line. It says run this command. Makes it really easy for you. Copy that line, paste, and hit enter. And it will start downloading PyTorch, installing it, Torch Vision, and the CUDA toolkit, which is the lower level libraries needed to do PyTorch machine learning. The next step is to download the PedalNetRT code, which we already did. So to get this document. So we can skip that step and go to downloading the SmartGuitarPedal plugin from GitHub as well. And what this plugin does is it will load in the trained model once we convert it, and you can play your trained model, whether it be from an amplifier or a pedal. You can play this through the plugin, and hopefully it will sound very close to the hardware that you trained it on. So we're going to go to this site, to the SmartGuitarPedal page, release page on GitHub, and we're going to download the SmartPedal VST3. And this is a plugin that can be played in any digital audio workstation, DAW. So we're going to take that file and put it in whichever location that your DAW uses to run VSTs. Now I've already done that, and I'll just show you what it looks like. I use Reaper, the Reaper DAW. So I'm opening up the effects page, going to the VST3, list of VST3 plugins, and I'm clicking on the SmartPedal that we just downloaded. So there it is. Once we train a model, we can load it through this drop down, and some very, very basic settings, drive and level to modify what that model sounds like. So I'll close this for now, and then we'll get into the model training portion of this project. So now we're going to get into using the PedalNetRT repository to actually use PyTorch to train these models. Now the training data that we're going to use for our model is already located in the PedalNet repository that you downloaded earlier underneath the data directory. There we have 2 WAV files, and it's important that these WAV files are in floating point 32 format as opposed to int16. That has to do with how the audio data is stored, and for real-time applications we want that floating point 32. If you have your own recordings that you've made, you can, I'll quickly show you how to make sure that that data is floating point 32 in Reaper. So if you select a track and you go to File, Render, then you can output a WAV file in the correct format. We want to remove this tail, or basically remove any additional data besides just the audio. We want to make sure that that is mono, so 1 channel. Make sure it's in 44,100 hertz, 44.1K. Output format, WAV. WAV bit depth, that's where you choose the 32-bit floating point, 32-bit FP, as opposed to any of the other options. I use this force wave option. Make sure that none of these other options are selected. Don't embed a tempo, write BWF. All of these things need to be unselected so that you only have the audio data in this file. And then you click render, and it will export that to a file that you can put through the PedalNetRT training. I'm going to bring back up the instructions, PedalNet instructional document. First step, make sure you do the steps in the previous document. So we are going to go into the PedalNet folder. For this tutorial, we're going to use the WAV files automatically included in the PedalNetRT repository. But if you have your own recordings, if you've created your own training data, then you can use that as well. And if there's interest in that, I can make a separate video that goes into the recording process that I used to get that data. So the next step, we're going to open up an Anaconda prompt by going to start typing Anaconda. It should come up. Click on it, and we have our Anaconda prompt. Now we're going to navigate to our PedalNetRT directory. There it is. And we're going to cd change directory into that folder. So I'm just copying the path to the PedalNetRT folder and typing that in there, and that's cd space and then the path. So now we're in there. If you type dir, then you'll get a list of all of the files in there. So the first step is type in Python space prepare _ data.py. This script will take the data in the WAV files and put it into what's called a Python pickle file, which is just a different format for the data that makes it easy to understand by Python. So we're going to do prepare data space, and then we're going to give it the path to the in TS9 test1n WAV file first, and then the second argument is the output, and hit enter. So now you can see that it generated this data.pick file with all of the audio data in there that can be used by Python. The next step is to, we're actually ready to train now. So Python space train.py, and we're going to hit enter and see what happens. Now I know I'm going to get an error here, and you may as well, and that's based on the GPU that's on my computer. It doesn't have, it's not a high-end GPU. It doesn't have a lot of memory available to it. So I want to show you this error in case you get it as well. So it said runtime error right here, cuda out of memory. So to fix that, we are going to give an additional argument to Python train.py, 2 dashes, and we're going to change the batch size that goes into the training model. So batch _ size equals, the default is set at 64. We're going to set it at half that at 32. And if you have to go even further down, take that down to 16, but it will take longer for training with those smaller batch sizes. So I'm going to hit enter, and we'll see if that works. You may get a lot of, you may get some warnings related to NumPy. Those are okay for now. Probably need to update something in the future. And now PedalNet is training training a model on our data that we input. The default setting is set at 1500 epochs. And as you can see, we just finished the first epoch, so it will take a while on this particular computer. If you're a gamer and you have a high-end GPU, this will probably be much faster. This is a standard Acer Intel i5 laptop. It has NVIDIA GeForce graphics card in there. Definitely not a high-end model. So this takes a long time, and I usually close the computer and let it run overnight or something like that. So in the interest of time, and because I'm not prepared at all, we're going to stop the training right there and just use that model that we trained through 3 epochs, which will not be very accurate at all. So you'll get to see what a bad model looks like. So we're going to take that trained model, and we're going to run the test script. Python space test.py. And we need to input the model that we just trained. Go into lightning logs, choose the appropriate version. This version 0 was generated when we did the first run through and we got that error. And the second one is the one that was working. So we're going to go into that. Go into checkpoints, and there's our trained model. It lists the epoch that was saved into that checkpoint. So if you get all the way through 1500 checkpoints, it may not say, it probably won't say 1500. It'll be something, it should still be a high number, maybe at least above 1,000, depending on how the model was trained. So we are going to input that, that model checkpoint into our test script and hit enter. And that will generate it's running the model through our test portion of the data from that data.pickle, file. So if we go back into the main directory, we should soon see 3 wave files. There they are. The test data is the portion of the data that that we're using to test our trained model with. So xtest is the original input data without the pedal or amp applied to it. And ytest is the input data that has the pedal or the amplifier sound applied to it. In this case, it is the TS9 Tube Screamer pedal. It's an iconic pedal that has a very recognizable distortion quality to it. People like Stevie Ray Vaughan used a previous version of the pedal here. So because we only ran this training through 3 epochs, it was a very poorly trained model, so this prediction should not sound like the final result. Which it doesn't. It has a little bit of a distorted quality to it, but it has a long way to go before it's trained to that, that other model. So now we're going to run the analysis script, which is type in Python plot_wave.py, plot_wav.py. Hit enter, and that will automatically look for those test wave files that we just generated. And it's going to give us some plots. I'm going to ignore this spectrogram plot for now and look at this. I'm going to look at this wave comparison plot. So at the top level, we have our original input, the wave file. And then in the second plot, we're plotting against the y-test and the y-predicted, which if we did full model training, they should be very close. Whereas with this model that we only trained for a couple epochs, it's very, very off, which is what we would expect. So the next step for making this into a model that we can use in the SmartGuitarPedal is converting our model into a .json model, which we can upload into the SmartGuitarPedal. So that command is, that script is Python convert PedalNet to WaveNet VA.py space. We're going to input our trained model checkpoint into that. So that's -- model equals lightning, and we're just going to navigate to our checkpoint file. and hit enter. And now we should see a converted model.json file. And this is you can read this by opening it up in any text editor. And you can, it's on one line, so it's not very readable, but the points of interest are at the very beginning, where you have your hyperparameters, which has to do with the layout of our model. So now we're going to take this, I'm going to rename it into something recognizable. So for this, since we trained it on the TS9 Tube Screamer, I'm going to name this TS9. I'm also going to note the epoch, which was 1. So it's a very poorly trained model. But we're going to take this and copy it into the executable for our DAW. In my case, that's Reaper. So I'm going to go into, where is Reaper stored? Program files, Reaper x64, and there's my Reaper executable. If you have a shortcut on the desktop, you can right-click that and go to Properties and see where that's pointing to find where your actual executable is. And I'm going to paste our new model into that same directory. Probably going to need admin rights. Hopefully that's not a problem. And so now it's in the same directory, so the VST will know where it is. So now, when we open up Reaper and open up our SmartPedal, we should be able to see that model. And I don't have my audio interface connected to it at the moment, so that's why we got that error. And I'm going to go to my FX view. I'm going to reload the SmartPedal so that it can pick up that new model. And I'm going to go to the drop-down, and here's our poorly trained TS9 model. It's this TS9 Epoch 1. There it is. Click on it, and then you can connect your audio interface and your guitar like you would for any other plugin and play through that. Now, if you want to see the end results of a properly trained model, you can go to the my other video showing a demo of the SmartGuitarPedal, and I select a few different models and play live through that plugin. And that's the whole process. It's really very simple to use, pretty advanced machine learning to make digital copies of your amplifiers and pedals. If you have any questions, post them in the comments, and I'll try and answer those the best I can. Thank you all for watching.